In this class we don't present any new theory, but rather just work some problems using energy methods. So to begin with, when we see a problem, which method do we want to use? Well, conservation of energy is usually the easiest method if you have only conservative forces. And for the problems we've been working in class, that means that only weight and springs are doing work on the particle. If we have friction involved, then that's a non-conservative force, so we have to use the method of work and energy. And usually we'll also use that when we have applied forces there as well. It just tends to be easier to think of that rather than try to understand where the datum is for an applied force as opposed to a weight. So again, conservation of energy, usually we'll use that only when weights and springs are doing work. Now, important to remember that if I need time, neither one of those methods is going to give me that, because they're relating forces and displacements directly to velocities. So you can always use the equations of motion if time is required. Remember that both work and energy and conservation of energy are derived from the equations of motion. One set of problems that we work quite a bit when we look at conservation of energy is in roller coaster problems. Roller coasters are very low friction, and so we usually ignore any friction. And so as a car drops from, in this case, from A to B, then what happens is as the car drops, then it's losing potential energy, and that potential energy, because again energy is conserved, becomes kinetic energy increase. So the speed increases, of course, from A to B. Well, usually we want to find what are the g-forces that the riders would feel. In other words, what's the normal force between the rider and his seat, or between the car and the track? And we get those using the equations of motion. We take the sum of the forces in the normal direction, set that equal to the mass times the normal acceleration, which of course is related to the speed, the normal acceleration being v squared over rho, the radius of curvature. A similar problem might be one where we have the roller coaster car going around a loop, and we might ask what's the minimum speed that will make sure that we get around the loop. And for that, we have to make sure that there is a normal force between the car and the track at B, so that force doesn't drop completely to zero. Once we do that, of course, that normal force relates to a normal acceleration, and the normal acceleration again is v squared over rho, so that'll define the minimum speed that I need to have at B to get around the loop. And if I know that, then you can work backwards and say I know what the minimum speed at A needs to be, because again I'm going to lose speed as the potential energy increases from A to B. The speed's going to drop accordingly. Problems that involve spring come up every now and then as well. And in this case, if I've got a crate that's going to hit this spring and I want to know how much the spring is going to compress, if there's no friction, then we can use conservation of energy. The kinetic energy of the crate, as it comes to a stop, will be transferred entirely to potential energy in the spring. On the other hand, if we do have friction, then we have to use the method of work and energy, or the equations of motion, of course, because in this case the friction force does negative work as the crate slides into and through the deflection of the spring. And finally, we also mentioned power and efficiency in this series of classes. Power we define as the force times velocity in the same direction, hence the scalar product here. The units of power are work per time, so in the US system it would be foot-pounds per second, but often we'll want to convert that into horsepower, and 1 horsepower is 550 foot-pounds per second. In the SI system, the units of work are Newton meters, and so power is in Newton meters per second, and a Newton meter is a joule, and a joule per second is a watt. And finally, we introduce efficiency as being the ratio of power out to power in. So for example, an electric motor, the work that can be done per time is the output power of the motor, and the electrical power in would be, of course, greater than the power out, because efficiency of any machine motor is always going to be less than 1. So you always have to put more power in than you get power out because of losses such as heat and friction, etc. So that kind of wraps that up. In the next class, after test 2, we'll talk about the method of impulse and momentum, which also includes looking at impacts between multiple particles.